Welcome back, students. Let's resume 6.2, the standard normal probability distribution. Here we go. In the previous video, we went through the standard normal random variables and the standard normal table, the z-table. From the z-table, we went through these two typical types of problems. Type 1, finding out the probabilities when the z-scores are given. Type 2, vice versa, finding out the z-scores when the probabilities are given. Now, we will continue our discussion about these two types, forward and backward, this time for arbitrary normal random variable. In order to do that, we have to take an extra step called the standardization. And here is the standardization formula. Z equals to x minus mu over sigma, where mu is the expected value and sigma is the standard deviation. This formula, by the way, is the one I usually call the formula number 1 of this entire course, because this is the most important formula by none. That includes, by the way, some variation of it, especially in the denominator, because if you deal with some sample study, we have to use standard error instead of standard deviation. But in any case, especially in terms of theory, everything is coming from the same thing. Very same normalization theorem. Okay, here we go. X is a random variable with the expected value mu and the standard deviation sigma. Then the random variable given by z, like this, x minus mu over sigma, has the mean 0 and the standard deviation 1. By the way, we established it and proved it in chapter 5 for discrete case. Here is the proof for the mean. As you can see, the expected value of z is 0. This is a bit trickier. Here's the proof for the standard deviation. The variance of z is 1. So upon taking square root, we get the standard deviation is also equal to 1. Proving the same thing for continuous random variable is going to be a bit trickier. But let's just take it for granted because this course is not calculus based and we need calculus to prove it. That doesn't mean we cannot use it. We'll simply adopt this formula as I said early on. The particularly interesting case is when x is a normal random variable. In that case, the standardized normal random variable given by this z equals to x minus mu over sigma has to be the standard normal random variable, which we studied in detail in the previous video. By the way, what exactly does it mean by standardization? In my opinion, the best way to see it is through rescaling. For example, how do you convert a temperature in Fahrenheit into the Celsius temperature? For example, if you have 85 degrees in Fahrenheit, this is what you do. Subtract 32 because 32 degrees Fahrenheit is equal to 0 degrees Celsius. And scale factor is 1.8. And calculate it, that gives you approximately 30 degrees Celsius. And how does that help? Well, we have two different numbers, but does that mean we have two different temperatures? In terms of Fahrenheit versus Celsius, we have different numbers. In terms of how hot it is, the same. For example, let's make an association with the probability with this Celsius Fahrenheit example. What is the proportion of the days with high temperature, 85 degrees or higher, here in DFW region in a year? And what is the proportion of the days with high temperature, 30 degrees Celsius or higher? Aren't they the same thing? Well, yes, indeed, they are the same. Or approximately the same, because 35 degrees is approximately equal to 30 degrees Celsius. And first proportion is this one in terms of Fahrenheit. The second proportion is that one. In terms of Celsius, they have to be the same. And of course, if you use several decimals to get really accurate Fahrenheit to Celsius measurement, then you have to have exactly the same equality, not approximate equality. Here's another way to see it. This one, capital Z is capital X minus mu over sigma, is the standardization of the random variables. And this one is the z-score. And as you can see, we follow exactly the same scaling, x minus mu over sigma, something minus mu over sigma. Consequently, the blue one associated with capital X and small x versus the red one associated to capital Z and small z must be exactly the same because we are changing the scale, the measurement, exactly the same fashion. Still not convinced? Well, I can give you a precise mathematical proof like this, but I don't know how many people would be interested in this. In any case, it is possible to rigorously prove it. Let's come back in more realistic sense. We'll have just this standardization formula, x minus mu over sigma, z equals x minus mu over sigma. That'll allow us to change problem given in arbitrary normal random variable into standard normal random variable, which you can solve using the z-table. Let's look at it in a little bit more detail through this example problem. Suppose that the mean and the standard deviation of normal random variable x are as follows. The mean is 16.75. The standard deviation is about 0.451. And about this probability that x is less than 16.01, how do you measure it? How do you estimate it? 16.01 is less than 16.75, the expected value. So the normal picture associated this random variable x must be centered at 16.75, the expected value. This one is a little bit to the left, and then capital X is still less than this, so we'll have to have left-hand side wing, kind of like this one. Yes, the left-hand side picture. This picture, left-hand side picture, is directly related to the problem. And of course, if you standardize this picture using the standardization formula z equals x minus mu over sigma, then you can re-express the same thing to the standard normal picture. And what z-score do you get? It turns out you're going to get negative 1.64. Well, indeed. All you have to do is this computation, x minus mu over sigma. Punch your calculator, and then you get negative 1.64. And the probability that z is less than that, wait a minute, we have done this before. This is exactly the same as part A of example 2.3. Let's pretend we don't remember, and let's just do it over. Negative 1.64, negative 1.6, and then 4, here it is, 0.0505. That is the probability. In short, we can use z-score formula to change into z, and then using the original picture, you can find out the probability using the z-table. Other probabilities, pretty much the same. Here's the picture. Yes, x is greater than 17.03, and the random variable x, or excuse me, the density function of the random variable x must be symmetric with respect to the expected value 16.75, and 17.03 is a little bit bigger than that, so to the right hand side x is bigger even than that, so we have further shading to the right hand side. We have this kind of picture in the left hand side, and find out the z-score using x minus mu over sigma, the standardization. And then what do you get? We get 0.62. So what do we get? We get the same picture, but with this z-score this time. And you know all about finding out the probability when you have the standard normal. Open up the standard normal table and then go to the second page and get 0.62, yes, 0.7324. This is not the answer because this picture, as you can see where my mouse is not the same as, well, any of these. Actually we need what? Complement. So we have to do this one, 1 minus 0.7324 and calculate 1 minus of that, so we get 0.2676. We have done this before. Draw the picture, get z-score, use your brain, you can do it. The third picture, again, pretty much the same thing, third problem. Between 16.01 and 17.03, we have two z-scores, z1 and z2. Calculate those using the z-score formula, x1 minus mu over sigma, x2 minus mu over sigma. Calculate those, and once you have those z-scores, use your brain, use your z-table, you can do it. Green minus blue, yes, we have done this before. How about the backward problem? Okay, pretty much the same thing too. Let's look at problem C, for example. We went a bit light about problem C in the previous set, so let's use this one. The probability that capital X is between 16.75, the expected value, and X is 0.275. So the area of this red region is 0.275. In order to get something for the z-table, we need all the way to the negative infinity, so you have to add the left hand side, 0.5. So we have to add up 0.5 and 0.275, so the probability is 0.775. Okay, where is 0.775 in this table? 0.775, 0.77. Well, here we go. 0.7734, 0.7764. It's got to be somewhere in between. 0.775 must be somewhere in between. So the z-squared estimated is 0.755, approximately speaking. And yes, indeed, this is a little bit more accurate figure. 0.755. In that case, you get probability 0.775. Alright, how do you calculate your x value from here? Well, z is x minus mu over sigma. Solving for x, you get that, and then that, and then here's the computation. As a matter of fact, I used really precise figure given by Mathematica, but the estimation I got using my z-table was only up to 0.755. So let's use only up to 0.755. In that case, what do you get? Yeah, pretty much the same thing. So let's estimate it as 17.09. How about an alternative way? Maybe some students may not like to do this, may not want to get this symbolic computation done. They want to solve numerical equation right away. Okay, in that case, z-score, which is x minus 16.75 mu over sigma 0.451, is going to be approximately equal to 0.755 approximately. Solving this, what do you get? X minus 16.75 is approximately equal to 0.755 times 0.451. Consequently, x is approximately equal to 16.75 plus this product. And if you calculate it, well, in the end, of course, you're going to get the same value because this is the same computation. That's another way.